Okay, let's have a look. So click those Chromebooks all the way closed, put all your distractions away, phone should be away, notes out, and let's take a look. We're gonna add one little piece today. So we're gonna extend the stuff we were doing with simplifying radicals. Let's start off, let's go ahead and just do kind of a warm-up problem here. What are we gonna do? What are we gonna do on this problem? So we're gonna subtract 2. We're just following order of operations. We're isolating x. We can point to a single x. So we subtract 2 from both sides. Now what? Divide. Good. We don't distribute, right? How come? We got an exponent. Good. Okay, so once again, I don't want to say this every day, but I do not want to see when I'm up here. I'm going to start getting a little irritated about this. I don't want to see earbuds. I don't want to see phones. Those better be away. Okay? For your own good. Okay, we're dividing by 2. And then what do we get over here?
20. Oh wait, 50.
Okay, so now what? Square root. Good. So we're checking these off. We subtracted, we divided, now we're up to exponents. So we're undoing the squared, right? And that gives us what? What do I have to include? Plus or minus. And what am I going to do with that square root of 50? Okay, I've got it right. I've got to factor it, don't I? I've got to simplify that. 50 is not a perfect square. So what are factors of 50? Now, we can choose different factors, but can anybody name probably the best 2 factors? 5 and 10 work, and we'll do this 2 ways. So let's compare. You tell me which one ended up being better. We can do 50, we could do 5 and 10. 5's prime, then what do we do with the 10? Okay, that works. Then we end up getting a couple of 5s and a single 2. Okay? Okay, we could also do 25 and 2. I would argue, to me, I like that way better. Slightly. They both work. But what's the advantage? Okay, good. We found a perfect square factor. And so right away we can see things. We can see that we're going to get a couple out of the 5 and 5, right? So it's always easier when you're breaking something down if you can, and you're out your target. Your goal is always to find things. The biggest perfect square factor you can as one of the 2 numbers that branches out from your original number, right? It works if you don't do it that way too, but it's just quicker and easier. Okay? So then this one's going to split up into 5 and 5. And there's our couple, there's our single, whoops, next. There's our single. It would work even better. Yes, ma'am?
Okay, so on like the 50 where you did 5 and 10, how can you tell that those 2 5s are coupled? Or like is it just...
On this one right here?
Yeah.
Because when we're at the end of each branch. So this was the end of a branch because it was prime.
Okay.
These are the ends of branches. So you just look at the ends of branches.
Sometimes that when I like do like the longer version, it was like the same ones but they're not couples. So that's why.
That can happen, right? So you can end up getting like 3 5s or something, right?
Mm-hmm.
Then you only keep 2 of them in a couple. One of them ends up being a single then. Okay. Let me give you one more illustration of the point I just made. So what if we were doing like 72? I could do 72 a bunch of ways. I could do 72 as 6 and 12 or 8 and 9, right? What if I did 6 and 12? Then that's going to break up into 2, whoops, it's going to break up into 2 and 3. This is going to break up into 2 and 6 maybe, and that breaks up into 2 and 3. So eventually I get couples, whoops. I get couples, and there's a couple, and there's a single, right? And so I'd end up with the square root of 72 equals 3, this thing's really lagging today, 3 times 2, those are my two couples, right? Times square root of 2, which gives me 6 times the square root of 2. So we got there, but can anybody see a much easier way, quicker way? What would be the best choice of factors for 72? 8 and 9 works, but there's even a better one. Now, when I say perfect square, does everybody know what I'm talking about? So let's make a list of perfect squares. 2 squared is, 3 squared is, 4 squared is. Okay, you get the idea? What's next?
49.
etc., right? Those are perfect squares. So I'm looking for perfect square factors. 36. Yeah. What if we did 2 and 36? 36, bingo, right? That's a perfect square. What's that break up into? 6 and 6, right? So look how quick we get to our couple and our single if we do it that way, right? One step. Yes?
So you don't have to break it down into paragraphs?
No, you don't have to. I mean, there's no point. If we break the 6 down into 2 and 3 and this one down into 2 and 3, what am I going to get? A couple of 2s and a couple of 3s. Well, that's just going to give me 6, right? As soon as I get a couple, I don't have to go any further, right? The earlier the better. You have to do it that way? No. Is it better? It's easier, quicker, okay? Okay, so continuing on then. So we got an answer. We got a couple of 5s and a single 2, right? So 5 times the square root of 2. Okay, what would the last 2 steps be then to get the x by itself? Subtract 5. So if we subtract 5, I'm going to put the negative 5 there in front of the plus or minus. And then what? Last step. Divide by 5. Okay, so if we divide both sides through by 5, when I divide this side through, I'm not going to get a common denominator though, because I've got 2 terms that are not going to combine. So I'll make them separate. So I've got negative 5 divided by 5. And then remember, when I'm doing the plus or minus term, we're dividing by a positive, so it's not an issue this time. But if I were dividing by a negative, for the plus or minus one, I don't need to make it negative. I'm already getting both signs anyway. So we always make it easy and just always divide by the positive, no matter what. So we can simplify then. Negative 5 over 5 is negative 1. And then what can I do to reduce here? 5 times the square root of 2 divided by 5. Yeah, the 5's cancel, right? Those are factors that cancel. So I just end up with plus or minus the square root of 2. So those are my 2 answers right there. One for the plus, one for the minus. Okay? All right, so good, good. Next issue though. What happens when we need to divide square roots? Because that's going to come up, we're going to do a problem like that in a second. So we got to develop this skill. So what do? Well, first of all, when we can, we want to take advantage of this. We know that the square root of A divided by the square root of B, if we want to, we can write that as the square root of A over B. That goes both ways. If we have the square root of a fraction, I can break it up into the square root of the top over the square root of the bottom, either way. Okay? But what this allows us to do is I could look at the fraction 121 over 50 and I could maybe reduce it. In this case, it doesn't reduce though, does it? Right? We're stuck with 121 on top and we're stuck with 50 on the bottom. So next step is we're just going to do what we can to start with on the top and the bottom. We'll simplify both the top and the bottom as far as we can, and then we'll go from there. So what is the square root of 121 simplify to? That's 11. That's a perfect square. Okay. What about 50? Let's make our little table. Let's try to be smart about this. Can you see a really good factor? 10 and 5 works. 25 and 2. If we do 2 and 25, we like 25 because it's a perfect square. Yeah, there's my 5 and 5. So I got a couple and a single. So we get 5 times square root of 2. Okay, but we can't leave it like that, right? We can't leave a radical in the bottom. We're supposed to rationalize the denominator. We're going to get rid of any square roots in the bottom. Can you think of a way to do that? Remember the trick? What do we do? How are we going to undo that square root? Okay, that works, right? If I multiply, what's the square root of 2 times the square root of 2? It's 2, right? If I multiply something by itself, what am I doing? Yeah, but like if I multiply 6 times 6, what do we call that? That's 6 squared. If I multiply something by itself, I'm squaring it. So the square root of 2 times the square root of 2 is just the square root of 2 squared, which cancels the square root, right? Okay, but I don't want to change the decimal value of my answer, right? The value of my answer needs to stay the same. If I were to punch this into a calculator without simplifying it, I would get a decimal answer back from my calculator, right? After I do my simplification, when I change this thing to look prettier, if I push the answer into the calculator, shouldn't I get the same decimal back? Doesn't that make sense? I mean, I want to get the same answer, I just want it to look differently. In the same way that if you get an answer like, let's say you get 9 over 6 as an answer, what is that as a decimal? As a decimal, it would come out to be 1.5, right? But that's not simplified. What would my simplified answer be? You already said 3 over 2, right? So they look differently, thanks. They look different, but they give us back the same answer in a calculator, don't they? You see my point? So when we simplify something, the value has to stay the same. We're just going to make it look better, right? So the same thing has to be true up here. So that was a great idea. The idea that we could multiply the bottom by the square root of 2 is awesome, because that's going to get rid of the square root of 2 on the bottom. But I can't just do that to the bottom, or I'm going to change my answer. How could I fix this so I end up with the same answer I started with? Do it to the top. Because then I'm multiplying by something divided by itself. What is the square root of 2 divided by the square root of 2? 1. If I multiply by 1, I don't change the value, right? That's our identity number for multiplication. You multiply by 1 and things stay the same, right? But let's see what does happen. So if I multiply straight across, on the top I'm just going to get 11 times the square root of 2. On the bottom I'm going to get 5 times, what's that going to become? 2. So 5 times 2 is, there's our answer, right? And we can't reduce that. Okay? See how that works?
You can't leave square roots on the bottom.
No.
On the bottom, leave them on top.
Top's fine. Can't leave one on the bottom. Okay? That's not fully simplified. We call this rationalizing the denominator. We don't want right now it's got an irrational number in the denominator, a square root, right? When we get rid of the square root, we end up with a rational number in the bottom, which is what we want. Yes, sir?
On the bottom, it's just like 1.5 times 2.
Yeah, so the bottom's just 5 times 2. Right. So as a rule, really simple rule, if you have a stranded radical on the bottom, stranded square root on the bottom, you just multiply the top and bottom by whatever the stranded square root is on the bottom. And that solves it. Then you simplify. Let's try another one. How about this? Can we do something to this before we even try to mess around with the square roots? Yes. What can we do? Ah, good. We could divide by 3. So we could write this as the square root of 6 over 99, which reduces to the square root of what? 2 over 33. So now we'll break it up into the square root of the top and the square root of the bottom. So we have a stranded square root on the bottom. Can I simplify the square root of 33? Is that gonna work? If I do a factor tree for 33, what do I get? 3 and 11, that's as far as I can go. No couples, right? You probably maybe had a sense right away that that wasn't gonna work. What was going on in your brain? What did you see about 33 that probably told you that we're not gonna be able to reduce that, simplify that radical?
It doesn't break down anything like the three, right?
3 doesn't break down, and neither does 11, right? But you probably looked at 33 right away and said, that's not gonna work, right? And you may not even know for yourself what you were thinking, but I bet you were. You might have been, starting to get a hint of that, right? This is what you were thinking about. That list we made of perfect squares, none of those divide into 33, do they? Right? If none of those divide into the number, none of those are a factor of the number you're starting with, it's never going to reduce. Right? The only way it's going to reduce is if one of these is a factor. Right? 72 worked because 36 was on that list. 50 worked because 25 was on that list. 33 doesn't work because none of those numbers divide into 33. Okay? So maybe you're starting to see a shortcut. So we're stuck with the square root of 33. Obviously, we can't reduce the top. We're stuck with that. So what do we have to do to rationalize the denominator? Multiply top and bottom by what? Square root of 33. What's that going to give us on the bottom? 33. Right? That just undoes the radical. On the top, what are we going to get? Square root of 66. And once again, we could try to reduce 66, but it's not going to work. There's no perfect square that divides into 66. Yep.
So why do the square root of the radicals cancel each other out on the bottom, not on top? Right?
Because on the bottom, we've got the square root of 33 times the same square root. Right? So that's the same thing as the square root of 33 squared. On the top, they're different. Okay? Okay, so let's try this in one problem. And then we'll let you work on this stuff. So this looks familiar. What are the steps we're going to go through? What do we do first? Subtract 12, good. So we get 5 times quantity 3x plus 4 squared equals what? 416? Okay, now what? Divide by 5. Uh-oh. That doesn't reduce, does it? Right? So now, when I square root both sides, what's going to happen? 3x plus 4 equals plus or minus square root of that. Right? So we got to simplify that. What's going to be the square root of 416? Well, let's make our little table for 416. Little factoring tree. What's a number that divides into 416? 2 does. We could do 2. 4 does too, doesn't it? Because 4 is going to go into 400, and it's going to go into 16, right? So if we do 4, 2 would work, it'd be fine. If we do 4, we're going to get 104. Obviously, that 4 is going to break up into 2's and 2's, right? Let's leave it as a 4 for now, just in case another one pops out. Okay, then we could have a couple of 4s. We can always go back and finish it later. What about this one? Does 4 go into 104? Should, shouldn't it? Goes into 100, and it goes into 4. So 4 goes into 10 2 times with 2 left over. 4 goes into 24. 6, okay? And then 26, we're going to be stuck, aren't we? That's going to give us, what, 2 and 13? But look, there's our couple. There's our singles, right? You see there, we could have gone further with the 4s, but why go further if we can just leave them as 4s, right? Instead of having 2 pairs of 2s, 2 couples of 2s, just 1 couple of 4s. So we get on the top 4 times square root of what? 26. 2 times 13. Divided by the square root, because we're square rooting both sides, right? Square root of 5. So we simplified the top, bottom couldn't be simplified. What's going to be our recipe for rationalizing the denominator?
Times 5 squared.
Square root of 5 over square root of 5. Okay, and then we end up getting what? 3x plus 4 equals plus or minus 5 on the bottom. What are we getting on the top? 4 times the square root of 26 times 5. So that's what, 130? And we can try to simplify that. Is it going to work? Not going to. Let's see, 2 and 65. 65 is going to be 5 and 13. So we're stuck, right? No couples. So that's the simplified radical. Now what are the last two steps? Okay, good. Subtract 4. We'll put the minus 4 in front of the plus or minus. Now what about this last step? Dividing by 3. Okay, dividing by 3 is the same as multiplying by what? Now, dividing by 3 is the same as multiplying something by 1 over 3, 1/3, right? Dividing by a number is the same as multiplying by its reciprocal. Why do I say that? Well, dividing by 3 is easy to do for the first term, because we're going to do these one at a time, aren't we? Because they're not going to combine. So the first one we'll just divide by 3, but the second one is already a fraction. It's kind of ugly to divide a fraction by something. So instead, we'll multiply the fraction by 1/3, right? Does that make sense? Accomplishes the same thing. So our final answer looks like negative 4/3 plus or minus. When you multiply fractions, you just multiply straight across. So the top is just 4 times the square root of 130. Bottom is just 5 times 3 is 15. And that's it. Can't go any further. Okay? Make sense? All right.